The wind cut different across the high plains of central Wyoming. Pierre Mercier learned that his first week in the Bighorn country during the winter of 1842, when he woke with his back stiff as iron and ice crystals forming where his body met the frozen earth. He had made his bed exactly the way every trapper in the Rocky Mountains was taught. Buffalo hide spread directly on the ground, buffalo robe on top, standard and trusted. By dawn, he could barely move his hips, and the cold had pulled heat from his body all night into ground frozen solid at minus 30 degrees Fahrenheit. Across the frontier, mountain men were losing sleep and suffering frostbite using the same proven method in the same brutal conditions. Over the following weeks, Mercier quietly combined techniques from indigenous camps and immigrant craft traditions to create a sleeping system that kept him warm when others shivered and used half the firewood. What did he understand about ground heat loss that every serious outdoorsman should know? The Bighorn Mountains rose like frozen teeth against a sky that hadn't seen warmth in 3 weeks. Prairie grass lay brittle and wind-scoured across the high plains, snapping underfoot when men walked to gather firewood or check trap lines. Ground freeze extended down past 18 inches, hard as granite, and the nightly temperature drop began each evening at sunset like clockwork, plunging toward minus 30 degrees Fahrenheit or worse. This was country that killed the unprepared and tested even seasoned mountain men who thought they knew winter. Pierre Mercier had arrived in this region with 15 other trappers in late November of 1842, part of a fur company operation working the beaver streams that fed into the Powder River system. At 38 years old, he carried the compact build and steady hands of a man who had spent 2 decades in canoe country, first as a voyageur hauling trade goods through the lake systems around Montreal, then learning wilderness travel on the long portages that connected the fur routes. He knew how to read weather, manage gear, and survive in conditions that broke softer men, but the high plains winter was teaching him that experience in one landscape didn't always translate to another. The morning after that first brutal night, Mercier found 3 men in camp unable to move properly. Tom Whitley couldn't bend his left hip where the cold had locked the joint during sleep. Sam Morrison had dark patches on his shoulder blades that would later blister and peel. Another trapper, a quiet Kentuckian named Davis, spent 20 minutes by the fire just trying to get feeling back in his lower back before he could stand upright. All of them had followed the same method that worked for mountain men across the Rockies. Spread 1 or 2 buffalo hides directly on the earth, add a buffalo robe with the fur side facing inward, and sleep. The logic seemed sound. Buffalo hides were available from recent kills. The setup required minimal effort when exhaustion hit after long days checking trap lines, and the method allowed quick camp breakdown when weather or game movement demanded travel. Most trappers carried this bedding system because it balanced weight against warmth, or so the thinking went. But here on the wind-stripped prairie, where ground cold penetrated deeper and held longer than in mountain valleys, the standard approach was failing consistently. Mercier's own background gave him perspective that his companions lacked. During his voyageur years around the Great Lakes, he had worked alongside Métis guides who mixed French woodcraft with indigenous techniques, learned from Ojibwe and Cree hunting parties. He remembered watching these men build sleeping platforms from cedar boughs and layer multiple materials under their blankets, especially during winter transport runs when camps had to be made on snow-covered ground. The principle was simple: create barriers between the human body and the earth that would pull heat away through direct contact. Later, at a summer rendezvous near Fort Laramie, he had spent 2 evenings drinking with Duncan McGregor, a Scottish immigrant who had worked as a woodsman in the Highlands before heading west. McGregor described how Highland shepherds built sleeping platforms in stone bothies during winter, using layers of heather, wool, and hides to stay warm on cold floors. The Scotsman emphasized elevation and air gaps, explaining that even an inch or 2 of space beneath a sleeping surface could prevent the earth from drawing away body heat through conduction. But Mercier had also observed something closer to his current situation. 2 summers earlier, while trading at a Lakota camp near the Black Hills, he had noticed how winter teepees incorporated raised sleeping areas built from willow frames and thick grass mattresses, covered with multiple buffalo hides. The indigenous families didn't simply throw robes on the ground. They engineered their sleeping systems with the same attention they gave to hunting equipment or horse gear. These memories surfaced as Mercier watched his companions suffer through their third consecutive night of poor sleep and morning stiffness. When Tom Whitley lost a full day's trapping because his hip wouldn't function properly, the practical cost became clear. In country where every day mattered for gathering pelts before spring breakup, injury from inadequate bedding was more than discomfort. It was economic loss that could determine whether a man returned east with profit or debt. The solution seemed obvious to Mercier, but implementing it brought immediate social friction. When he began collecting willow branches to weave a sleeping mat, several trappers made comments about his extra work. "Mercier's building furniture now," one said. "Why stack hay and hides when a hide on the ground is good enough for the rest of us?" The supply boss, a company man, named Caldwell, who managed equipment and rations, suggested that Mercier's approach represented unnecessary luxury that violated the efficiency principles that kept trapper operations profitable. This resistance puzzled Mercier because the techniques he planned to use weren't exotic innovations. They were established practices from other cold-weather cultures. But frontier trappers had developed their own traditions, and questioning those methods implied criticism of men who had survived previous winters using standard approaches. The social pressure to conform was real, especially when supplies were shared and group cooperation determined survival. Despite the mockery, Mercier began his modifications gradually. He cleared snow and debris from his sleeping area more carefully than others, then laid a coarse mat woven from willow twigs as his first layer. This created an air gap between his body and the frozen earth, but he quickly realized that the thin mat alone wouldn't solve the heat loss problem. His second night with just the willow platform showed improvement, less stiffness, no ice crystal formation where his back contacted the bedding, but he still felt cold seeping upward from below. The incomplete success revealed the central challenge. Conventional frontier wisdom treated ground contact as inevitable, while traditional knowledge from other cultures treated it as a problem to be engineered away. Over the following days, Mercier would need to build a complete system that combined multiple insulation principles. But first he had to prove that his alternative approach worked better than methods that had satisfied trappers for decades. The conflict between proven practice and innovative technique would play out in the practical laboratory of minus 30-degree nights, where failure meant frostbite and success meant survival. Mercier's third night revealed the core physics problem that his willow mat alone couldn't solve. Heat moved from his warm body into the frozen earth through direct conduction, following the path of least thermal resistance like water flowing downhill. The thin air gap created by the woven twigs slowed this heat transfer but didn't stop it, especially when his body weight compressed the mat and reduced the insulating airspace. He needed bulk insulation, a thick layer of material that would trap air and create genuine thermal resistance between his body and the ground that remained frozen at 20 degrees Fahrenheit, even when surface air temperatures climbed during brief afternoon warming periods. The solution came from watching a Lakota hunting party that had made temporary camp 2 miles downstream along Crazy Woman Creek. Mercier rode over on the fourth morning, ostensibly to trade for dried meat, but actually to observe their sleeping arrangements. Inside their canvas and hide shelters, he saw sleeping platforms built from willow frames, supporting thick mattresses of dried prairie grass, topped with multiple buffalo hides and blankets. The grass layers measured 6 to 8 inches deep, creating substantial bulk between the sleepers and the ground. An older Lakota man, noticing Mercier's interest, explained through a mixture of trade sign and broken English that grass trapped dead air, and that dead air was the best protection against ground cold. He demonstrated by digging into one of the grass mattresses, showing how the dried stems created thousands of small air pockets that wouldn't move or circulate. Moving air carried heat away from the body, but trapped air remained still and gradually warmed to body temperature, creating an insulating barrier. This aligned perfectly with knowledge Mercier had gained from Duncan MacGregor's descriptions of Highland sleeping arrangements. The Scottish woodsman had explained that peat mattresses worked because peat contained countless air spaces within its fibrous structure. When MacGregor built emergency shelters in the mountains, he would cut blocks of peat or gather dried heather to create thick sleeping platforms that prevented ground cold from reaching through to sleeping bodies. The principle was consistent. Bulk insulation with trapped air spaces provided thermal resistance that thin materials couldn't match. Armed with this understanding, Mercier began gathering dried prairie grass from areas where wind had deposited thick accumulations against rock outcroppings and fallen logs. The grass needed to be completely dry to work effectively, since moisture would freeze at night and create conductive pathways that would defeat the insulating purpose. He collected enough to build a layer 6 inches thick across his entire sleeping area, packing it densely enough to support his body weight, but loosely enough to maintain air spaces throughout the mass. The construction process took 40 minutes of steady work. First, he placed the willow mat on the cleared ground to create the initial air gap and provide structure for the grass layer. Then he spread the dried grass evenly across the mat, testing the thickness by pressing down with his hand to ensure consistent depth. The grass compressed under pressure but sprang back when released, indicating good resilience. Finally, he placed a buffalo hide directly on top of the grass layer, fur side down, to serve as both a vapor barrier and an additional insulating layer. This hide placement proved crucial for reasons Mercier discovered through trial. On his first night with the grass layer, moisture from his body had migrated upward into the grass during sleep, where it froze and created ice crystals that reduced the insulation's effectiveness. The buffalo hide on top of the grass prevented this moisture migration while adding its own insulating properties. The hide's natural oils also repelled moisture that might seep up from the ground below. The results became apparent immediately, on a night when the ambient temperature dropped to -32 degrees Fahrenheit and ground temperature held steady at 18 degrees Fahrenheit. Mercier woke without the hip stiffness and back numbness that had plagued him during previous nights. More importantly, when he placed his hand under his sleeping area in the morning, the grass layer felt warm to the touch while the ground beneath the willow mat remained frozen solid. He began taking systematic measurements to quantify the improvement. By pressing his bare hand against different parts of the sleeping system each morning, he could estimate temperature differences. The top surface of his sleeping area remained approximately 34 degrees Fahrenheit when the air temperature reached -30 degrees Fahrenheit. In contrast, areas of ground where other trappers slept registered around 15 degrees Fahrenheit by dawn, showing that the standard hide-on-ground method allowed massive heat loss throughout the night. The grass layer itself maintained an internal temperature of roughly 28 degrees Fahrenheit, demonstrating that it was successfully trapping and holding body heat rather than allowing it to conduct into the frozen earth. This represented a thermal improvement equivalent to the difference between sleeping indoors and sleeping outside, achieved through nothing more sophisticated than dried plant material and proper layering technique. Meanwhile, his companions continued struggling with the standard approach. Tom Whitley developed a persistent cough from the stress of cold nights, and Sam Morrison's shoulder blade frostbite progressed to painful blisters that interfered with his trap-setting work. The economic cost of their poor sleep became measurable. Men who spent the first hour after waking trying to restore circulation and mobility couldn't start their daily trap rounds until the sun was well up, reducing their effective working time and limiting their access to the most productive dawn and dusk periods when beavers were active. Supply boss Caldwell noted these inefficiencies in his daily logs, but attributed them to the harsh winter rather than inadequate bedding systems. He calculated that the camp was running through firewood at nearly double the expected rate because men built up fires each morning to combat the effects of poor sleep, then maintained larger fires throughout the day to dry gear and warm stiff joints. The additional wood gathering required 2 men to spend half of each day cutting and hauling fuel instead of working trap lines. Mercier's system eliminated most of these secondary problems. He woke each morning with normal body temperature and joint flexibility, allowing him to begin work immediately. His reduced need for warming fires meant he contributed more time to productive trapping activities while consuming fewer camp resources. Within a week, his trapline productivity exceeded that of any other man in the group, despite using identical trapping techniques and working the same quality of a beaver habitat. The foundation layer was now complete and proven, but Mercier recognized that ground insulation alone wouldn't solve every heat loss problem during extended cold periods. His next challenge would be managing the heat that escaped upward from his body into the cold air above, requiring a completely different set of traditional techniques focused on creating effective barriers to convective and radiant heat loss. 2 nights after perfecting his ground insulation system, Mercier discovered that solving one heat loss problem had revealed another. A shift in weather patterns brought sustained winds across the high plains, and these winds created convective cooling that pulled heat away from the upper surfaces of his bedding. Unlike conductive heat loss, which moved through direct contact with solid materials, convective heat loss occurred when moving air carried away the warm layer that formed just above his body during sleep. The wind came from the northwest, steady at 15 miles per hour, with gusts reaching 25 miles per hour. This created a wind chill effect that dropped the apparent temperature to minus 45 degrees Fahrenheit, even when the actual air temperature measured minus 30 degrees Fahrenheit. The moving air constantly swept away the warm microclimate that should have formed in the space immediately above his sleeping area, preventing his body heat from accumulating in a protective layer. Traditional mountain man bedding wasn't designed to address this problem. Most trappers simply pulled a buffalo robe over themselves and accepted whatever warmth it provided. The robe offered substantial insulation when air remained still, but moving air penetrated through gaps at the edges and carried away heat from the exposed surface. Mercier noticed that his companions frequently woke during windy nights to adjust their robes, fighting a losing battle against heat loss that occurred faster than their bodies could generate replacement warmth. The solution required understanding how different materials responded to air movement. Wool blankets, which Mercier had acquired through trade with emigrant families heading west along the Oregon Trail, possessed structural properties that buffalo hide lacked. Wool fibers created a matrix of tiny air pockets that remained stable even when external air moved across the surface. These trapped air spaces couldn't circulate or carry heat away, unlike the larger air gaps that formed between a person's body and a loosely draped hide. Mercier's wool blanket measured approximately 4 feet by 6 feet and weighed 3 pounds when dry. The wool had been woven with a loose weave that created substantial loft. The blanket maintained a thickness of nearly 2 inches when laid flat. This loft was critical because it meant the blanket contained a large volume of trapped air relative to its weight. When he placed the wool blanket directly on top of his grass sleeping platform, it created an insulating layer that moved with his body rather than allowing air gaps to form and shift during sleep. But wool alone couldn't solve the complete problem of upper body heat loss. The blanket's outer surface remained exposed to wind, and moving air still carried away heat through convective cooling. This required an outer shell that would block wind while preserving the insulating properties of the wool layer underneath. Buffalo hide served this function perfectly when positioned with the fur side facing outward. The physics of this configuration worked through multiple mechanisms simultaneously. The wool blanket trapped air and prevented internal circulation that would carry heat away from his body. The buffalo hide above the wool blocked external wind from penetrating to the insulating layer. The fur on the hide's outer surface created additional dead air space while also reflecting radiant heat back toward his body instead of allowing it to escape to the cold sky above. Mercier discovered the importance of this radiant barrier during a clear night when temperatures dropped to minus 38 degrees Fahrenheit. On clear nights, his body lost heat through radiation to the cold sky, which acted like a massive heat sink. The night sky temperature effectively measured much lower than air temperature, sometimes reaching minus 60 degrees Fahrenheit or colder. Without a reflective surface to redirect this radiant heat loss, his body constantly lost energy to the vast cold dome above. The buffalo hide fur addressed this by creating a reflective surface that bounced radiant heat back toward his body, rather than allowing it to escape to space. The dense fur fibers trapped additional air while creating multiple surfaces that reflected heat internally. This radiant barrier function worked independently of the hide's wind-blocking properties, providing 2 distinct types of heat retention in a single material. Assembly of the complete upper insulation system required specific sequencing to maximize effectiveness. First, Mercier placed the wool blanket directly on his grass platform, ensuring no air gaps existed between the blanket and the foundation layer. Next, he positioned himself on the wool blanket and drew it around his body, creating a continuous insulating envelope with minimal openings. Finally, he pulled the buffalo hide over the entire assembly, fur side outward, and secured the edges to prevent wind from lifting or penetrating the outer shell. This layered approach created what amounted to a personalized insulation system with 3 distinct thermal zones. The grass foundation prevented conductive heat loss downward into the frozen ground. The wool blanket prevented convective heat loss from his body core by trapping still air in immediate contact with his skin and clothing. The buffalo hide shell prevented both wind penetration and radiant heat loss to the sky above. The windbreak component required additional consideration of campsite positioning and local terrain features. Mercier began selecting sleeping locations that placed natural barriers between his bedding and the prevailing wind direction. A cluster of large boulders or a grove of willows could reduce wind speed across his sleeping area from 15 miles per hour to 5 miles per hour, dramatically decreasing the convective cooling effect on his buffalo hide shell. When natural windbreaks weren't available, he constructed temporary barriers using available materials. A framework of willow branches covered with spare hides could redirect wind flow and create a calm pocket of air around his sleeping system. These windbreaks didn't need to be large or elaborate. Even a partial barrier that reduced wind speed by half provided measurable improvement in heat retention. The results became apparent during the first full night with the complete upper insulation system in place. Ambient temperature reached minus 36 degrees Fahrenheit with steady winds, but Mercier slept through the entire night without waking to adjust his bedding. In the morning, when he placed his hand on the inner surface of the wool blanket, it felt warm and dry. The outer surface of the buffalo hide showed frost formation, indicating that heat was staying inside the system rather than escaping to form frost on the inner surfaces. His companions, still using single buffalo robes, continued to struggle with interrupted sleep and morning stiffness. Joe Harris reported waking 4 times during the same night to readjust his robe after wind had shifted it or cold had penetrated through gaps. Sam Morrison's persistent cough worsened as interrupted sleep reduced his resistance to the respiratory stress of breathing extremely cold air. Mercier's wool consumption calculations showed the economic value of better sleep. He estimated that his improved rest allowed him to work at full efficiency for 9 hours daily, compared to 6 or 7 hours for men who spent recovery time each morning dealing with the effects of poor sleep. Over a trapping season, this difference translated to approximately 30% more productive time, which meant 30% more pelts and 30% higher profits from the expedition. The complete envelope system was now proven and refined, but Mercier recognized that even perfect insulation could fail if moisture infiltration compromised the material's effectiveness. His next challenge would involve managing vapor, condensation, and the freeze-thaw cycles that could destroy the carefully engineered thermal properties of his multi-layer sleeping system. 3 weeks into January of 1843, an unexpected warming trend disrupted the stable cold that had allowed Mercier to perfect his sleeping system. Daytime temperatures climbed to 15 degrees Fahrenheit, causing surface snow to melt and refreeze each night into a glassy crust that reflected moonlight across the prairie. This daily freeze-thaw cycle introduced a moisture problem that threatened to destroy the insulating properties Mercier had worked so carefully to achieve. The moisture infiltration occurred through multiple pathways that hadn't existed during the steady cold periods. Melting snow created ground moisture that wicked upward through capillary action, seeking any porous material that would absorb it. Daytime humidity from the melting process condensed on cold surfaces during the nightly temperature drops. Most critically, the temperature differential between Mercier's warm body and the fluctuating external conditions caused water vapor from his breath and perspiration to condense within his bedding system rather than escaping to the outside air. When moisture penetrated the grass insulation layer, it froze during the coldest pre-dawn hours and formed ice crystals throughout the dried plant material. These ice crystals created conductive pathways that allowed heat to flow directly through what had previously been effective insulating material. Mercier discovered this problem when he woke with familiar cold spots on his back and hips, indicating that his foundation layer was failing despite his careful construction techniques. Examination of the grass layer revealed the extent of the moisture damage. Ice crystals had formed along individual grass stems, connecting them in a network that conducted heat efficiently from his body to the frozen ground below. The total weight of ice within the grass increased the layer's mass by approximately 4 ounces, but more importantly, the ice altered the thermal properties of the entire system. What had been dead air spaces filled with trapped warmth became pathways for rapid heat transfer. The solution required understanding vapor transmission and implementing barrier techniques that Mercier had observed during his time with Métis hunting parties near Lake Superior. Those mixed heritage trappers used birch bark sheets as vapor barriers in their winter shelters, positioning the bark to block moisture movement while allowing necessary air circulation. In the high plains environment, buffalo hide could serve the same vapor barrier function if positioned correctly within the insulation system. Mercier's modification involved adding a second buffalo hide between his grass foundation and wool blanket. This inner hide was positioned with the flesh side facing downward toward the grass and the fur side facing upward toward his body. The flesh side of the hide had been treated with brain tanning processes that left natural oils in the leather, creating a surface that repelled water vapor trying to move upward from the ground. The fur side provided additional insulation while maintaining the vapor-blocking properties of the hide beneath. Installation of this vapor barrier required rebuilding his entire sleeping platform with precise attention to sealing. The inner hide needed to overlap at all edges to prevent vapor from bypassing the barrier through gaps or seams. Mercier tucked the edges of the inner hide under the grass layer, creating a sealed envelope that prevented ground moisture from reaching his wool blanket and upper insulation layers. This configuration maintained the thermal properties of each layer while blocking the moisture transmission that had degraded the system's performance. But vapor barriers created a new problem by trapping moisture from his own body within the upper layers of the sleeping system. During sleep, an adult human produces approximately 1 pint of water vapor through respiration and perspiration, even in cold conditions. Without proper ventilation to remove this internal moisture, it would condense on the inner surfaces of his bedding and eventually freeze, creating the same ice crystal problems he was trying to prevent. The ventilation solution came from indigenous knowledge that Mercier had learned while observing Lakota winter camps. Teepee designs incorporated controlled air circulation that removed humid air without creating disruptive drafts. The key was managing air exchange at the edges of the sleeping area, while maintaining still air within the insulation layers themselves. This required elevating his entire sleeping platform to allow air circulation underneath, while creating small ventilation gaps that would permit moisture-laden air to escape. Elevation of the platform involved constructing a raised frame using available deadfall timber and willow branches. Mercier built a simple framework that lifted his sleeping system approximately 3 inches above the ground surface, creating an air gap that extended completely under the platform. This elevation served multiple functions simultaneously. It allowed air circulation that carried away ground moisture before it could reach the grass layer. It provided ventilation space for humid air to escape from the edges of his bedding, and it further reduced conductive heat loss by increasing the air barrier between his body and the frozen earth. The framework construction used dead logs as primary supports, positioned lengthwise to span the width of his sleeping area. Smaller willow branches laid crosswise on the logs created a platform surface that supported the willow mat and grass layer without sagging. The entire framework required approximately 30 minutes to construct using materials gathered from nearby timber debris, and it could be quickly disassembled for camp moves. Ventilation management required careful attention to wind direction and airflow patterns around the sleeping area. Too much air movement would create drafts that defeated the insulation properties, while too little air movement would allow moisture accumulation. Mercier positioned the head of his sleeping platform toward the prevailing wind direction and left small gaps at the foot end where humid air could escape without creating cross drafts through the insulation layers. The controlled ventilation system worked by creating gentle air circulation that removed moisture-laden air while maintaining the thermal properties of the insulation materials. Cold, dry air entered near his head, gradually warmed as it passed around the edges of the sleeping area, picked up moisture from his breath and body heat, and exited as warm, humid air at the foot of the platform. This circulation occurred slowly enough to avoid disrupting the still air within the wool and hide layers, but fast enough to prevent moisture accumulation and condensation. Testing of the moisture control system occurred during a week-long period when daily temperatures reached 20 degrees Fahrenheit and nightly temperatures dropped to minus 25 degrees Fahrenheit. These fluctuating conditions created maximum stress on the vapor management components. Each morning, Mercier examined his bedding materials for ice crystal formation, moisture accumulation, and overall dryness. The results demonstrated significant improvement in moisture control. The grass layer remained dry throughout the test period, with no ice crystal formation visible when he separated individual grass stems for inspection. The wool blanket maintained its loft and insulating properties, showing no signs of moisture penetration or freezing. Most importantly, the inner surfaces of both buffalo hides remained dry, indicating that the vapor barrier was successfully blocking upward moisture migration, while the ventilation system was removing internal moisture before it could condense and freeze. Comparative measurements showed the effectiveness of the integrated moisture management approach. Mercier estimated that his sleeping system now retained approximately 90% of its dry condition thermal performance, even during freeze-thaw cycles, compared to roughly 50% performance for unmodified grass or wool insulation exposed to similar moisture conditions. The weight of ice formation within his bedding system dropped to less than 1 ounce per night, compared to 4 ounces during the initial moisture infiltration problems. His companions continued to struggle with moisture-related insulation failures. Their buffalo robes absorbed ground moisture during warm days and froze solid during cold nights, creating stiff, uncomfortable bedding that provided minimal thermal protection. Several men developed persistent coughs from sleeping in damp conditions, and the constant moisture cycling degraded their buffalo hide bedding to the point where replacement became necessary. The complete sleeping system now incorporated 4 integrated components: ground insulation, upper envelope protection, vapor control, and ventilation management. Each element supported the others in creating a microenvironment that maintained optimal thermal performance regardless of external weather fluctuations. This systematic approach represented traditional knowledge refined through practical testing, proving that engineering principles could be applied successfully using frontier materials and construction techniques. The ultimate test of Mercier's integrated sleeping system arrived during the final week of February 1843, when a massive Arctic air mass settled over the high plains and refused to move. For 5 consecutive days, ambient temperatures held steady between minus 35 and minus 40 degrees Fahrenheit, with sustained winds creating wind chill equivalents that plunged to minus 60 degrees Fahrenheit. Ground freeze penetrated to 30 inches depth, deeper than anyone in the camp had experienced, and supply caravans from Fort Laramie were delayed by weather too severe for travel. This extended cold snap created survival conditions that pushed every piece of equipment and every survival technique to absolute limits. Firewood became critically scarce as men burned through reserves trying to maintain minimal warmth in their shelters. Water sources froze solid, requiring constant fire maintenance just to melt ice for drinking. Most seriously, the extreme cold began causing equipment failures that threatened the entire trapping operation's viability. The 15 men using standard buffalo hide bedding suffered progressive deterioration in their physical condition as the cold snap continued. By the 3rd day, 5 men showed clear signs of frostbite on their backs and hips, where prolonged ground contact had overcome their body's ability to generate replacement heat. Tom Whitley and Sam Morrison could no longer perform their daily trap checks because joint stiffness prevented normal movement for the first 3 hours after waking. 2 other trappers, including the quiet Kentuckian Davis, developed what appeared to be early hypothermia symptoms: confusion, slurred speech, and persistent shivering that continued even when they sat directly beside fires. Supply boss Caldwell documented the deteriorating situation in his daily expedition logs, recording fuel consumption rates that threatened to exhaust the camp's firewood supplies before the cold snap ended. The standard bedding method required each man to maintain large warming fires from before dawn until mid-morning, just to restore normal body function after nights of inadequate sleep. Collectively, the 14 men using conventional techniques burned through 3 full cords of firewood during the 5-day period, consuming wood faster than 2 men could cut and haul it even working full-time. Medical emergencies compounded the resource crisis. The two men showing hypothermia symptoms required constant fire warming and supervision, removing them from productive work entirely. The five men with frostbite needed daily treatment and wound care, reducing their effectiveness for trapline maintenance. By the fourth day, only 7 of the 15 conventional sleepers remained capable of full workloads, creating a labor shortage that threatened to leave traplines unattended and reduce the expedition's total pelt harvest. Mercier's performance during this same period demonstrated the practical value of systematic insulation engineering applied under extreme conditions. He maintained normal body temperature and joint function throughout the cold snap, waking each morning with sufficient energy and mobility to begin work immediately. His fuel consumption remained minimal because he required only small fires for cooking and equipment maintenance, not for body warming. His daily firewood use totaled approximately 1/5 of a cord during the entire 5-day period, saving roughly 2 1/2 cords compared to the standard approach. More significantly, Mercier's consistent sleep quality allowed him to maintain peak mental alertness and physical coordination when others were suffering from cold-induced impairment. He continued checking his full trapline circuit daily, while others reduced their coverage or worked in pairs for safety. His trap productivity during the cold snap actually exceeded his normal rates because beavers concentrated in the few remaining unfrozen water sources, making them easier to locate and catch. The economic implications became clear when Caldwell calculated the expedition's overall performance during the critical period. The 7 men still capable of full work harvested approximately 40% fewer pelts than expected because reduced trap coverage allowed many beavers to escape or relocate. The additional firewood costs, calculated at frontier labor rates, added the equivalent of $50 to expedition expenses. Medical care for frostbite and hypothermia cases consumed supplies and supervision time equivalent to another $30 in lost productivity. Joe Harris, the fellow trapper who had previously expressed interest in Mercier's methods, made a direct request for instruction on the 3rd day of the cold snap. Harris had developed severe hip stiffness that prevented him from mounting his horse without assistance, making trapline travel difficult and dangerous. Mercier spent one afternoon teaching Harris the complete system construction, emphasizing the integration between ground insulation, envelope protection, vapor barriers, and ventilation management. Harris's first night using the modified system produced dramatic improvement in his condition. He woke on the 4th morning with restored joint mobility and reported sleeping through the entire night without waking from cold. His immediate recovery validated the techniques in front of the other trappers, who had witnessed Harris's deteriorating condition and dramatic overnight improvement. 3 more men requested instruction from Mercier before the cold snap ended. Supply boss Caldwell visited Mercier's sleeping area on the final morning of the extreme weather, examining the construction details and asking specific questions about material requirements and assembly time. Caldwell measured the fuel consumption difference by counting the quantity of unused firewood near Mercier's shelter compared to the exhausted wood piles around conventional sleeping areas. The visual evidence convinced him that the systematic approach offered genuine operational advantages rather than mere personal comfort improvements. When supply caravans resumed travel after the cold snap ended, Caldwell placed orders for additional wool blankets and extra buffalo hides, specifying quantities sufficient to outfit the entire trapping party with layered bedding systems. His requisition request included detailed notes about the economic benefits observed during the extreme weather test, providing company management with quantified justification for the additional equipment investment. The knowledge transfer process accelerated throughout the remaining winter months as more trappers adopted Mercier's techniques and began teaching them to others. By spring of 1843, the systematic sleeping approach had spread to 3 other fur company operations working the Powder River drainage. Men who learned the system during their first winter taught it to incoming trappers the following season, creating a knowledge transmission network that operated independently of formal company training. Documentation of the techniques appeared in fur company field manuals by the late 1840s, though often without attribution to Mercier or acknowledgement of the indigenous and immigrant knowledge sources that informed his innovations. The published instructions emphasized practical construction details and material specifications rather than the underlying thermal principles, but they preserve the essential technical information needed for successful implementation. Later 19th century frontier guides incorporated refined versions of the multi-layer insulation approach, often describing it as established best practice for winter camping in extreme conditions. Military manuals for Western expedition forces included similar techniques by the 1860s, suggesting that the knowledge had spread beyond civilian trapping operations to influence formal survival training programs. Modern backcountry camping guides rediscovered many of the same principles during the mid-20th century, though using synthetic materials rather than buffalo hides and prairie grass. Contemporary sleeping system designs achieve similar thermal performance through factory-manufactured components that replicate the insulation, vapor barrier, and ventilation functions that Mercier engineered using frontier materials and traditional knowledge. The legacy extended beyond camping techniques to influence broader understanding of systematic approaches to frontier survival challenges. Mercier's integration of multiple knowledge traditions, indigenous, immigrant, and practical frontier experience demonstrated that innovation often emerged from combining existing techniques rather than inventing entirely new approaches. His documentation through teaching and his students' transmission of complete systems rather than isolated tricks preserved both the technical details and the underlying principles that made systematic solutions more effective than improvised responses to survival challenges. The sleeping system that kept one French-Canadian trapper warm during the winter of 1843 became a foundation for systematic wilderness survival knowledge that influenced frontier practice for generations and continues to inform modern backcountry techniques today.